You see, when you take derivatives, I showed you some bulletproof techniques that are in the book, and basically you just you take a derivative using the techniques that we talked about. There's a chain rule, there's some other things, but essentially, in order to take a derivative, you just keep taking derivatives, going on the inside, on the inside, on the inside, multiplying everything together as you go until you finally end up with nothing else to take a derivative of. And there's some other things like the division rule, the multiplication rule and stuff, but really it's pretty mechanical to take a derivative. You just have to know what to do. Integration, you will see, is much more challenging. For the basic ones like we're going to talk about today, it's not going to be a big deal. I'm going to show you the basic rules. But as we go along, you will see that there are some integrals that you're going to shake your head at and you're going to say, how do I do that? Okay. In fact, in real life, in engineering and in physics, there are plenty of integrals that you can't even solve, period, without a computer. They're impossible to solve. So here's when you start to get into math that really becomes challenging. I'm going to do my best to explain the basics to you and so that you'll have a good foundation so that you can move along. Now recall, in order to develop this idea of what an integral is, I'm going to kind of use an analogy from what we've already talked about, which is the derivative. Okay? Remember back at the very beginning when I said, okay, here's a function of x and it's x squared. Okay? And I asked you to say, well, let's take the derivative of that, f prime of x, and you already know now that that's just 2x. Okay? So when you go from here to here, okay, we say that that's taking, I'm going to write it like this, a derivative. I'm going to write it right there, derivative, when you go from there to there. And that means that that's the slope of the line tangent to this curve at whatever point you're interested in. Now what if I give you the function 2x and I ask you, what function of x would you need to arrive at such that if you take the derivative of it, you get this? In other words, how do you go backwards from here to here? That's really the question I'm asking. Okay? When you do this, this is called taking an integral. Okay, in fact, another word for an integral is an antiderivative. Okay, it truly is just the opposite of a derivative. So you already know how to go from a function to the derivative. Okay, now you're going to see a lot of problems when I give you a function and you're going to go the other way and you're going to go back to the original function and you're going to take the antiderivative, or otherwise known as an integral. Okay, and you might say, well, geez, what the heck is that useful for? Who cares? Well, we're going to do some examples and show you why it's useful. But integrals are everywhere in engineering and physics. You can't go a day without seeing them. Okay, so when you do this, okay, it's called the antiderivative. Or the integral. Okay, it's the same word. Okay, so the way you would write this in a problem is it would be the integral, which is a funny symbol, looks like kind of like an S, okay, of 2x over dx. Okay, and you would say this is taking the integral of some function, and you would say that that's equal to x squared plus a constant, c, and I'll explain why we put that there here in just a second. But what you have on the left is you have this funny symbol called an integral. You have something in the middle that you're taking the integral of. In this case, it's this function 2x, okay? And you're integrating over some differential variable. I know I'm using a lot of terms that don't mean anything right now, but basically it's called a differential variable dx. You know, before when we took dy with respect to dx, it's the same dx there. It's a very small value of x is really what it means, okay? And so you're integrating this function with respect to x is really kind of what that means, okay? And when you do that, you arrive at basically at x squared plus a constant. We'll talk about it in a second. And in this case, you know the answer because I already told you that the derivative of x squared is 2x, and so going backwards is really easy because you already know the answer. I have not told you the mechanical means to actually calculate this. We're just doing it by means of an example. Now, why is this true? Okay, why is this true? Because if I take x squared and I take the derivative of it, what I get is 2x back. So what you're trying to find when you take the integral is a function such that if you were to take that function and take the derivative of it, you get back what you started with. It's just the same thing as here. If you take the integral of this, you arrive at x squared. And this function, which is the answer, is a function such that if you take the derivative of it, you get back what you started with. That's the definition. That's why it's an antiderivative. Okay? So the derivative of x squared is 2x. Now looky here. The derivative of x squared plus 10, what's this equal to? Well, it's equal to 2x. What is the derivative of x squared plus 57,000? Well, again, this is a constant, so it goes away. So every time I take the derivative of this function here, which we're saying kind of is the answer, I get the same thing back, 2x in all cases. So that is why when you take the integral of something here, like this, you write it down, you know what the answer is, but you always have to add a constant to it. And this is an arbitrary constant. This means this could be 1, this could be 10, this could be 50, this could be 1,000. It doesn't matter. It could be any number. That's why I put a letter there, and it's called C. It's a constant. So the reason we write it there is to remind us that the real answer to this problem is an infinite number of answers. These are just 3 of the answers, and they're all equally valid, because the only constraint is whatever I get on the right-hand side, I better be able to take the derivative of it and get back what's under here in the integrand, okay? So C can be any number, and so that's why we have to write it out like that. So anytime you take derivatives, like integrals like this, you will have a constant called a constant of integration that's going to be off to the side in your answer. Now, I want to make sure that you're aware that this kind of integral is called an indefinite integral. It's an indefinite integral, and the reason is, later on I'm going to show you what a definite integral is. That's really what the answer is. But in these, in this integral symbol here, if there are no numbers up here on the top and on the bottom, and you will see some here shortly on when there's some numbers up here, there's no definite definite bounds of the integration. It's just sort of a general problem with no definite bounds to it. And so we're doing kind of an arbitrary integration here without any definite bounds. I know that doesn't make much sense, but the thing I want to make sure that you're aware of is when you have an integral symbol with no numbers, it's called an indefinite integral. And later on, there will be numbers there, and I'll show you what to do with those, but that would be called a definite integral. Okay, let's just do one more quick, example, just to kind of make sure that you understand the concept. If I have the integral of 3x squared dx, I have not told you how to do this mechanically, so don't freak out because you don't know what the answer is. But I will tell you that the answer is x cubed plus c, plus this arbitrary constant. It could be anything. Okay? The reason is, so I'm going to put because x cubed, when I take the derivative, gives me 3x squared, which is what I started with. Because x cubed plus 49, for instance, some arbitrary constant, again, it goes away when you take a derivative of it. So when I take the derivative, again, I get 3x squared. So the answer to this integral is x cubed plus a constant, precisely because I can take the derivative of this and I get this back. That is the definition of an integral, and that's the most important thing that you need to be familiar with right now. So what we're going to do at this point is I'm going to erase everything that we had up there, and I'm going to write some properties of integrals down, just like we did in the beginning when we wrote properties of derivatives down. I'm going to write those properties down, we're going to talk about them, and then we're going to go work a lot of problems. And as I've already told you, I personally feel that working problems is really the best way to do this kind of stuff. Okay? So let's write some problems. Let's write some properties down here on the board. Okay. In general, if you have the integral of x raised to the power of n, this could be x cubed, x to the 5th, x to the 6th, integrated over dx, the answer, this is the mechanical means I was telling you, this is the way in which you will take integrals, is 1 over n plus 1 x to the n plus 1, plus, of course, a constant, which we always have to write down. Don't forget that. Okay? Now, there's a small catch here that you'll learn about later. N cannot be equal to 1. Whoops, cannot be equal to to negative 1. N cannot be equal to negative 1. And we'll learn about why later, okay? In fact, we're going to learn about that so far later that I'm just going to kind of erase that for now. This is the basic formula here. This would govern how you would take the integral of 3x squared. It would govern how you take the integral of 10x to the 5th. It would govern how you do all of that. So let me just give you a quick example of how you would use that. If you had integral of x to the 57th power, to the power of 57 over dx, well, you just use this formula. 57 is n, so you have 1 over 57 plus 1. You just add 1 to the exponent. X, put the x there, and then you add 1 up here. So that would be, again, 57 plus 1. So in the end, you would have 1 over 58x to the 58th. Okay? That is the answer. Of course, you can't forget, you got to have your constant of integration over to the side. If you forget to put those c's down, you're probably going to get points taken off on your test. So don't forget that. Why is this true? Again, I'm going to show you why is it true. If you were to take 1 over 57, or correction, 1 over 58 times x to the 58th power, and then you were to take the derivative of this, you should get back what you started with, right? Let's take the derivative of this. 58 comes out and gets multiplied, so what you have is 58 over 58x, and then it's the exponent minus 1 to take the derivative, so it's 57. And I think you can convince yourself what you'll have is x to the 57, because you have a 1 out here in the front. So you end up where you started with. Okay? So with derivatives, you end up subtracting 1 to get the exponent, and with integrals, you end up adding 1 to get the exponent. It's really the bottom line. Okay? This is the basic formula for how to integrate a polynomial. Another property, so I'm going to put a little asterisk here by the important properties. You might want to write these down as we go if you don't already have them in your book. If you have the integral of a constant times a function of x over dx, well, that's simply the following. You take the constant out, and then you integrate what's left over. That's very similar to a derivative. When it was a derivative, you take the constant out, and then you take the derivative. So it's the same thing. So an example of that would be integral of 4x to the 5th power over dx. Well, you've got a constant in the front, and you've got a function of x, x to the 5th. So really what you're doing here is you put the 4 out in front, and then you take the integral of what's left over. And I just showed you how to take the integral of x to the 5th. You use this formula. So what you would have here is 4 over 5 plus 1 is 6, x to the 6th. Because remember, it's 1 over n plus 1, okay? So I just have a 4 out, so I have the 4 on top over n plus 1, which is 6, x to the 6th, plus a constant. And of course, you could reduce this to 2/3 x to the 6th plus a constant. And you might want to pause the video now and prove to yourself that if you were to take this thing right here and take the derivative of it, you would get back what you started with, 4x to the 5th. So why don't you guys do that right here as we go. Shouldn't take you very long. Now another property, these are kind of the basic kind of no-brainer things. You could probably guess them off the top of your head. If you have a function of x and you're adding it to another function of x, we'll kind of call them f and g dx. Well, then the way to do that really is you just integrate the first one, f of x dx, and then you integrate the second one, g of x dx, or whatever these are, and then you just add the resultant integrations up together. Okay? So an example of that would be, let's take the integral of x cubed plus 4x to the 4th power dx. Now we have a function of x. I know how to integrate that one separately. Another function of x, I know how to integrate that one separately, but they're added up, so what do? Well, I just integrate each one and add the results. So what's the integral of the first one? Using this formula up here, it's going to be 1/4 x to the 4th. You'll see the pattern is very simple. It's 1 over 1 plus the exponent, x to 1 plus the exponent. Boom, you're done. Plus this guy, it's going to be the same thing, but I've got a 4, so the 4 is going to be on top. 4 over 4 plus 1 is 5. X to the 4 plus 1 is 5. So then you have that part of it. And then in the end, you have this constant left over. Now you might say to yourself, well, I'm going to have a constant associated with this integral and another constant associated with this integral. Why don't I have two constants here in the answer? Because after all, I'm adding up two integrals together. Well, the answer is, you're exactly right. You do have two constants. But a constant plus a constant, just gives me another constant. So this c here is really the sum of each of these two constants. And it really doesn't matter because, as I said, c can be anything at all. So you don't need to keep track of those constants separately. If you're adding two integrals up, you're only going to have one constant in the end. Okay, this board is basically geared at teaching you how to take integrals of polynomials. You start out with the basic one, and then I show you what to do when they're added together. So you might want to jot these things that are starred down and kind of keep them in your back pocket because we're going to use them a lot. But I also think that as we work problems, we're going to work a lot of problems here on integrals because it's a core topic. I think in the end it's going to become pretty clear. Okay, I just want to make sure that you're aware that if you remember back from the section on trig derivatives, if we have the sine of x and we take the derivative of it, we get the cosine of x. Right? Remember, I wrote a whole list of things down in a previous section that gave you all the derivatives of the trig functions, and the first one was derivative of sine was cosine. Well, from that, you should be able to convince yourself that the integral of the cosine function is equal to the sine function. Because I take the integral of this, I should get back this. Right? And then you always have your plus constant out over here. So I'm going to go ahead and write down basically all of these. Cosine of x, you take the derivative, you get negative sine of x. And if you remember back, tangent, integral of tangent is secant squared of x. A derivative of cotangent is equal to negative cosecant squared of x. The derivative of secant is equal to tangent times secant. And cosecant, the derivative of cosecant is negative cosecant cotangent, right? So these are pretty much the trigonometric derivatives. All right, now what I'm going to do is go ahead and write down the integral of all of these functions, just so you have them for your own records. Now you can probably find this in any old calculus book, but I'm going to show you where they come from. If we want to integrate the sine of x over dx, what would that be equal to? Okay, well, here I know that the integral of negative sine would give me cosine, because remember the integral goes backwards. If I integrated negative sine, I would get a positive cosine, but here I'm trying to integrate a positive sine, so the answer is negative cosine of x plus a constant. Okay, if I integrate the cosine function, I already told you that integral of cosine gives me positive sine. So I'm just going to write that one down. The integral of secant squared of x, which is here, is just equal to tangent plus a constant. The integral of cosecant, you see I have if the integral of negative cosecant squared would give me positive cotangent, well, because I have this negative here, this is going to be a negative cotangent of x plus a constant. The integral of secant x times tangent x, okay, and I forgot right here, you have to have dx. Secant tangent integral is going to give me secant of x plus a constant. And then finally, if I want to take the integral of cosecant times cotangent x dx, what would that be equal to? Well, if it were negative cosecant times cotangent I was integrating, I would get a positive here. But because there's a negative in there, there's going to be a negative here. Cosecant of x plus a constant. Now, the only reason I wrote all these on the board is not for you to memorize them. You're not going to memorize them. It's just mainly to show you how you go about calculating them. If you see a problem that's an integral of secant times tangent, maybe there's some other junk around there, you may freak out and say, well, I don't know how to do that. Well, you've already been given what the derivative of the secant function is, and so you already have the answer. Okay? You can get all of these directly from your list of derivatives, which I've already given you. So you don't have to do too much thinking, but you need to know what you can derive if you need to, on a test or on homework or whatever. So you can write these down if you like. They're probably in your book. I wanted to give you a list of trig integrals, okay, because I gave you a list of how to integrate polynomials. Okay, now the other thing I wanted to talk to you about, I've been talking about an integral in a kind of an abstract sense as far as is the fact that it's the opposite of a derivative, and that is exactly true. It is the opposite of a derivative. That's why we also call it an antiderivative, okay? But there's another meaning of an integral that's very important for you to understand, okay? Just like I gave you the meaning of a derivative was the slope of that line. You see, I didn't have to tell you any of that, but we did so that you would understand the point. Integrals have a meaning as well, and that's what I want to talk about next. Is kind of like the basic meaning of what an integral is. So I'm going to title this board, What Does an Integral Mean? Okay? In my layman's terms. I can tell you in words what it means, and you'll probably shrug your shoulders and say, well, okay, who cares? But eventually I'm going to go ahead and explain it to you. What does it mean? In words, it means it is the area under a curve. Derivatives is the slope of the line tangent to a curve. Integrals means that's the area under a curve. So let's figure out what the heck that means. Here is a graph here of a function. It goes like this. The function is y is equal to x squared. So this is a parabola, and of course it goes negative, and so on. So here at the value of 4, you know, goes up to there, and this is the value, obviously 0. Okay, the area under this curve, this area right here, the area, just like you would think area means, it is exactly like the area of a square or a rectangle. The actual area underneath this curve that would extend under this curve from 0 to 4 is defined by definition to be the integral of x squared dx. But somehow you have to indicate that you want to know the area only between these 2 points. So you put a number here, which means from 0, and a number here, which means 4. And this is what I was trying to tell you earlier. This is an example of a definite integral. Okay? So this is a definite integral. Okay? I'm going to put a reminder here for you. 0 to 4. Okay? It could be 10 to 100, it could be -3 to 5, it could be anything. But anytime you put numbers here, what you're asking is you want to define or bound this integral and only look at the area under that curve that you have here under the integral from certain 2 points. That's a definite integral. When you don't have any numbers here, it's an indefinite integral, and that's what we talked about earlier. Okay? Now, I haven't really given you the theorem that proves that this is the case, but I'm going to show you how to calculate this area under this curve, like in actual square centimeters or something like this. What you would do is you would integrate this just like you always do, and we showed you how to do that. It's 1/3 x to the 3rd power. This is the answer, okay? But then you have to draw yourself a vertical line to remind yourself that it's still being evaluated only from 0 to 4. There's no integral sign anymore because I've already done the integration. 1/3 x to the 3rd, that is the integral. But this vertical bar just reminds myself that I'm still evaluating this function that I've calculated from 0 to 4. Okay? To calculate the area, you take the number on the top and you plug it in. So you would have here 1/3 4 to the 3rd power minus, so what you have to do to finish this guy off is you'll have to plug in the value on the bottom on the right-hand side, so that'd be 1/3 0 to the 3rd power, like this, and then this whole term is going to go to 0 because 0 cubed is 0, and so it's going to be 0. So in the end, what you would have is 4 cubed, which would be 64 over 3. And that would be the answer. That would be the actual answer in area units underneath the curve there. Now, I haven't explained why this works. I haven't explained much about it. But basically, what you have done is you have already learned the fundamental theorem of calculus, and it really is called the fundamental theorem of calculus. And with a name like that, you would think it's pretty darn important. What it means is the integral, when you go from a to b, so you have a definite integral defined from a to b of a function f of x integrated over the differential variable dx, would be equal to the antiderivative, big F, evaluated at the point b minus the antiderivative, big F, evaluated at the point a. This is how you'll see it written in your books. Big F just means take the integral of it. It's the integral of f of x. You evaluate it at the upper point b, and then you subtract the same function evaluated at the lower point a, which is exactly what we did here. We took the integral. This is big F in this case. We evaluate big F at the top point, which is 4. We subtract big F, which is this, evaluate at the lower point 0. You do this calculation, do the subtraction, you arrive at the answer, which is the evaluation of that integral over those points, which in layman's terms is the area under this curve. Now, briefly, I just want to give you kind of a song and dance a little bit more deeply about what integrals mean, because it will help you as you go later on down in your studies of higher math. Okay, what you are really doing with this integral here is what you're doing is you're slicing this function up into an infinite number of slices like this. So if I were to draw like another curve here, I'm going to do it in red. And let's say we're going to approximate this function. Okay, so this dotted line is the real function. But if I were going to approximate it, I could have like a triangle here, a rectangle here, and a rectangle here, and a rectangle here, and then a rectangle here, and so on. And I can have little rectangles all the way up to the top, or to as far as I want to go. If I wanted to calculate the area under the curve, well, I could just simply look at the area of all the individual little rectangles, and I know how to take the area of a rectangle, right? It's just the width, right? Which you could just call delta x, would be the width of that rectangle. I know the height of this rectangle, which is f of x, and then I can multiply those two things together, and I'll arrive at the area of this little column here. And then I can do it for this one, and for this one, and for this one, and so on, and I can add them all up, and I can put them under a summation symbol. Now, I'm not going to write the whole thing out in all of its glory, but basically you could sum all of these things up, and you would get an approximation of the integral. It wouldn't be the real deal, because when you look up here, look at all this area I missed here. I didn't get any of this here. I didn't get any of this over here, and so on in between the little columns. I didn't get any of that area, so it's not really perfect. But if you think about it, I could take the limit as delta x approaches 0. In other words, make delta x very, 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 very small. So infinitesimally small that we don't even call it delta x anymore. We call it dx, okay? Which means a very, very small sliver of x. In that case, you would have a whole bunch of these columns. You would have an infinite number of columns because you make dx infinitely small, or delta x infinitely small, and then you add up all these things under the summation symbol, and then you would get a true representation of this area. Now when you do that, when you take the limit as delta x goes to 0 of this big fat sum of all of these little columns, this summation turns into an integral. So that is really the definition of an integral. It's the limit of an infinite number of sum of things, okay? In this case, they happen to be area, okay? And when you take that limit as delta x goes to 0, you get this integral. It's kind of the same thing as when we look at the slope of a function for the derivative, and we took the limit of the slope, and then we proved to ourselves that that became the derivative. Well, this is kind of the limit of an infinite sum of little rectangles, and they become an integral. So this is a fundamental theorem of calculus. You're going to use this all the time. Write it down, love it, know it, memorize it. It's not that hard. Geez, all it really says is you take the integral of the thing, and then you evaluate the integral at the endpoints and subtract them, and then you get the area under the curve. So as you might guess, one application of integrals is to calculate the area of things. You know, it's easy to calculate the area of a triangle or a rectangle or a square, but what if you had a curve that kind of goes like this, or like a vase or something, or a cardboard cutout of something that does this? How would you calculate the area of that? Certainly you don't know how to do that using the formula for the area of a triangle. Well, you could define the shape as a function, and then you could calculate the area of it using an integral. In fact, the area of a triangle, the area of a square, all that stuff can be derived and was derived using calculus.
Learn anything at mathandscience.com.